So it may seem a little out of line that we're going back to oxidation numbers now, but ideally you kind of remember how oxidation numbers are assigned from last semester general chemistry. So far we've been looking at metals that are solid and metals that have charges. So those oxidation numbers are quite easy. But there are lots of things that can be oxidized and reduced, so we're going to do a brief recap of what oxidation numbers are. First of all, here's the definition of an oxidation number. It's the charge that an atom would have in a molecule if electrons were completely transferred. Ionic compounds, electrons are completely transferred, but in molecules they're shared. But oxidation numbers pretend like electrons are completely transferred. They're always transferred to the more electronegative atom in a molecule. We'll see what I mean. So rule number 1 of oxidation numbers, free elements in their uncombined state have an oxidation number of 0. Some examples of that are sodium metal, potassium metal, lead metal, but all of these diatomic elements are also an oxidation number of 0. Next, in monatomic ions, the oxidation number is equal to the charge. This is the one we've seen a lot with our oxidations so far. Lithium has a +1 charge, so his oxidation number is +1. Iron, this iron has a +3 charge, so he's a +3 oxidation number. Oxygen almost always has an oxidation number of -2. The times where it doesn't is in H2O2 and O2 2-. In those two compounds, oxygen has an oxidation number of -1. When it's a diatomic up here in its uncombined natural state, it's a 0. Otherwise, oxygen is a -2. So all the group 1 metals, that's lithium, sodium, potassium, those are +1. Group 2 metals, calcium, magnesium, strontium, those are +2. And fluorine is always -1. The other halogens can change depending on what they're connected to, but fluorine is always -1. The oxidation number of hydrogen is +1, almost always, unless it's bonded to a metal in a binary compound. What the heck is that? If you have lithium hydride, the rule above this says lithium is always +1. So in order for this to be a 0 charge, and it has to be a 0 charge because there's no charge indicated up top, hydrogen must be a -1. If it's potassium hydride, potassium is +1, hydride -1. Other than being combined with metals like lithium, potassium things, hydrogen's a +1. The sum of the oxidation numbers in the atoms has to be equal to the charge on the molecule, or the ion. Let's look at one. According to our rules, oxygen always has a charge of -2. According to our rules, hydrogen always has a charge of +1 unless it's in a binary metal compound. So carbon was not part of our rules. Carbon is an unknown in this compound. So if we have 3 times -2, that's -6. Because there are 3 oxygens, and a +1. So if we write it in the order of the ion, it's +1 plus carbon's unknown plus -6, all has to equal -1. So if you do the quick addition subtraction there, carbon ends up being a +4 in this compound. Carbon is something that can have quite a lot of oxidation states. You need to use the things that it's bonded to determine carbon's oxidation state. So our last big electrochemistry topic is balancing redox reactions. In the previous reactions we've seen metals going from ions to solid or solid to ions. But there are many other varieties of redox reactions. Let's balance a couple of them. These are the rules we're going to follow. They're on page 815 of your textbook. But let's balance a reaction now. The oxidation of I- bipermanganate in acidic solution to yield molecular iodine and manganese 4 oxide. So reading that sentence, that's what we come up with. Step number 2 says separate the equation into 2 half reactions. What that means is write a half reaction for the similar species. So I'm going to separate iodine from manganese. There are my 2 unbalanced half reactions. But in order to continue, I'm going to need more space. So we're trying to balance these two half reactions. So if we focus on our left half reaction first, maybe we should specify, is this the oxidation or reduction half reaction? Over here, I minus is a -1. Here, it's a diatomic in an uncombined state. It's a 0. It lost electrons. So this is my oxidation half reaction. Must mean this is my reduction half reaction, and we can guarantee that by double checking our charges. Oxygen is a -2. -2 times 4 will give me a total of -8 from the oxygens. Manganese must be a +7 in order to counterbalance the -8 and give me a -1 charge overall. Oxygen is -2. -2 times 2 gives me a total -4. So this is manganese +4. Manganese went from +7 to +4. Manganese gained electrons. Okay, back to the balancing. Rule number 3 says balance the atoms other than oxygen and hydrogen in each half reaction. So I've got 1 iodine, 2 iodines, 2 I- yields I2. Manganese, 1 on each side. Okay. Step number 4, add water to balance the oxygen atoms and H+ to balance the hydrogen atoms. There is no oxygen, there is no hydrogen. This one's done. This one, I've got 4 oxygens on the left, 2 oxygens on the right, so add 2 waters to the products side. 2 waters brought in 2 oxygens, but it also brought in 4 hydrogens. So I need to add 4 H+ on the reactants side. Add electrons to one side of each half reaction to balance the charges in the half reaction. So over here on the reactant side, I've got a 2- charge overall. Over here, I've got no charge overall. So my electrons are going to get added to the products side to make my charges balanced. Do the charges have to be 0? No, the charges have to be equal. Reactants and products charges have to be equal, but not necessarily 0. Okay. On the product side over here, nobody has a charge, so that's a sum of 0. On the reactant side over here, I've got a +4 and a -1, so I've got a +3. I need to balance it out so they're equal. I'm going to add 3 electrons to my reactants side and bring the remainder of my equation down as is. Okay. If necessary, equalize the number of electrons in the 2 half reactions by multiplying half reactions by appropriate coefficients. So I've got 2 electrons on this side and 3 electrons on that side. This equation will only balance if those electrons are equal. So I'm going to multiply this equation by 3 and that equation by 2 in order to get them to balance. Multiply the whole thing and just bring it on down. Almost there. Add the 2 half reactions back together and cancel anything that will cancel. Cancel anything that will cancel. We definitely need to cancel out our electrons, and if we cannot cancel our electrons, we did something wrong. Nothing else cancels here. So our final balanced equation is 6I- plus 8H plus 2MnO4- yields 3I2 plus 2MnO2 plus 4H2O. Verify that the number of atoms and charges are correct. 6I, 6I, 8H, 8H, 2Mn, 2Mn, 4 times 2, 8 oxygen, 4 plus 4, 8 oxygen. No charge on the product side. 2-, 8+, 6-. Yep, both sides equal 0. Because my original problem said balance this in acidic solution, this is my final balanced equation because it's in acid. If it's in base, you have to do one more step. Ready for another one? So our next problem says balance this guy in basic solution. So the first thing we do is recognize it's not balanced and then separate it into half reactions. The two manganese pieces get pulled off to one side, and the two other pieces get pulled off to the other side. This is the exact same manganese setup as before, so this is my reduction half reaction. Must mean this is my oxidation half reaction. Who is it that's actually getting oxidized? Sulfur. Oxygen's -2, so -2 times 3, that's going to be -6. Sulfur must be a +4 to balance out the -6 and end up with a -2 charge overall. -2 times 4, that's -8. Sulfur must be a +6 in order to balance out the -8 to give you a -2 overall. So sulfur changes from +4 to +6. Sulfur is oxidized. Okay, balance atoms other than oxygen and hydrogen. One manganese, done. One sulfur, done. Balance the oxygen by adding water. MnO4- yields MnO2 plus 2H2O. Oxygen is balanced. Water plus SO3 2- yields SO4 2-. Balance the hydrogens by adding H+. 4H plus MnO4- yields MnO2 plus 2H2O. I'm going to take a shortcut on this one because I have space and say 2H plus. Get added to that one. After hydrogen come electrons. On the reactants side over here, we've got a +3 charge. We need to make it balance the product side, which is a 0. So 3 electrons plus 4H plus MnO4- yields MnO2 plus 2H2O. There's a -2 on this side and a 0 on this side because we've got a -2 and a +2. So this side needs 2 electrons, the product side. Balance out the electrons by multiplying if necessary. Multiply my oxidation half reaction by 3, my reduction half reaction by 2. So multiplying, we get 6 electrons plus 8H plus 2 MnO4 yields 2 MnO2 plus 4 H2O. 3 water plus 3 SO3 2- yields 3 SO4 2- plus 6 H plus 6 electrons. We're now ready to combine this pink one and this pink one. Recombine your oxidation and reduction half reaction. Let me clear up some space. So my recombined equation becomes 6 electrons plus 8H plus 2 MnO4- plus 3H2O plus 3 SO3 2- yields, this is a long one, 3 SO4 2- plus 6H plus 6 electrons plus 2 MnO2 plus 4 H2O. Maybe I'm just a giant writer. Cancel out anything that you can. That definitely means electrons every time. But this time you can actually cancel out more. You've got 8H plus over on the reactant side and 6H plus on the product side. So you cancel that and make this 2H plus. One more thing can be canceled. 4 waters and 3 waters, cancel it out and make it 1 water. So our equation with everything that can cancel canceled is this. We would be totally finished if this said balance in acidic solution, but it doesn't. It says balance in basic solution. So we have another step. For reactions in basic solution, add hydroxide to both sides for every H plus that appears in the final equation. So over here I've got 2H plus, so I add 2 hydroxide. 2 hydroxide. The reason for this is this hydroxide and H plus combines together to make water. So this simplifies to 2 waters. And then I can cancel out things one more time to get rid of my 1 water on the product side and leave 1 water on the reactants. So really, truly, we are finished this time. And this really large equation is our final balanced equation. Balancing redox reactions is not difficult, but you have to make sure, you have to make sure that you follow the steps in very particular order, or you'll end up goofed up somewhere and it's hard to track down your error. So this is really my final balanced equation. Whew. Done.